Hi everyone, welcome back to Coding with Bharat channel. So this week we are taking the new topic which is DQ topic or the double-ended queue. So yeah, let's get started with a question. We'll try to organically solve it with brute force and then see why this data structure comes into the picture here. So the question says, let's say we are given an array nums of some size n. Now, what we want to do is we want to look at each of the windows of subarrays in this nums array of size k. So as an example, if this is my particular nums array, right? So it has 3, 3, 6 and 2, 8 elements. And now I want to look at every window of size k. Size k is what? 3. So what are the different windows of size 3? First window would be 1, 3, minus 1. Next window would be 3, minus 1 and minus 3. Next window would be minus 1, minus 3 and 5. So on and so forth. So look at every window and calculate the maximum in it. So first window the maximum is 3. Second window again if we look at it the maximum is 3. Third window maximum is 5. Similarly you can continue. Fourth window is 5. Fifth window is 6. And finally last window is also 7. Okay. So this is the array that you want to return. So for every window of size k in order, the maximum for that subarray. Okay. So just pause the video for a moment and think of brute force here. I think you should be able to come up with that. Okay, let's get started with brute force. So simply saying, let's say we have some array 2, 1, minus 1, 3, 5, 7, minus 3. Okay, let's say whatever we have as k, let's say k is 3. What we can do is we can try to start a subarray at every point. So what I'll do is I'll start a subarray here, I'll start a subarray here of size 3. Right? Okay. Now what I will do is I'll run a loop k times and just take the maximum and put it in my result. So what I can do is I can simply run one loop for I equal to 0 to n minus. Okay. So if I think about it, if k is in fact 3, then can I start my array at n minus 1? Answer is no. Can I start my array at n minus 2? Answer is again no. Can I start my array at n minus 3? Answer is yes. So basically whatever your k is, you will not be able to start your array at the k minus 1 endpoints, right? So you'll just have to run this loop till n minus k. Another simple way, if this n minus k doesn't make sense, run till n, right? Run till n minus 1, which is the last. Calculate. If I do I plus k, is it going outside? If it is going outside, I'll break from there, right? That could be a simpler way if you don't want to do this mathematical calculation. Okay. What is a simpler way? Again, just to repeat, run this loop till n itself and then calculate, okay, j is equal to I plus k. If my j has become greater than equal to n, that means the end is outside the array length, so I can break from here. So yeah, for those of you who find this calculation n minus k confusing, just go ahead with this, right? It's perfectly okay. I'll stick to n minus k. Okay. So now that you have fixed the starting point, next step is go over the k elements and take the maximum of it. So I'll define maximum so far is equal to array of I. I'll start my j as I plus 1, right? And I'll need to do k steps, k minus 1, because I've taken one element already in my max. So I just need to do k steps, k minus 1 steps, right? So I'll make some number of steps. Let's call it steps equal to k minus 1. So these many steps times. So how do you do that generally? While steps minus minus. So these many steps times, take the jth element and increase j by 1. So I'll say maximum is equal to max of already existing maximum and array of j, and then do j plus plus. So go over the elements, put it into the max, and finally whatever the max you have, you put it into an answer array. So let's say we have a vector of answer. So what I'll simply do is, at the end of this while loop, every time I'll push the maximum that we found into my answer, right? So fix every starting point, take k elements, take the maximum, put it into your array. So if we think about the time complexity of this, then we'll come up with O of n into k, because we have n starting points. If you want to be more accurate, it could be n minus k starting points, but minus k would not make a difference. So we'll keep it at n. So for n starting points, you are doing an iteration of k. So in worst case, this will become n into k, which can actually go beyond the limit of the question. So if we look at the question, it clearly says that n and k can be huge. So 10 to the power 5. So n into k then becomes n square, which is kind of like not possible. Okay. So yeah, this is the brute force. I hope this is clear to everyone. So let's now think about optimizing it further. Okay. So let's optimize it. So let me go over one idea. Let's say we have an array, and in that array we have few elements, right? 2, 1, right? 4, 3, let's take 7. Okay, cool. Let's try to figure out if we have some useless elements that can never become my maximums, right? So let's take an example. Let's start with this 2. Okay, right now we don't care about other elements. It is our first element. It can very well happen that, like, let's say we don't even know k. It can very well happen that the window size is such that there are a few elements which are just smaller than this 2. So this 2 can possibly become your maximum, right? It can possibly become a maximum. Okay, cool. Let's say k is now 3. Let's take the next element 1. Okay, now we know about 2 and 1. 2 could have become maximum. Can 1 become maximum? Answer is yes, 1 can become maximum when it happens that, okay, let's say here it was 0 and minus 1. We don't know the future elements, right? So if it was like 0, minus 1, these kind of elements, then our 1 will actually become a maximum when we take a window of these 3, right? So we have to keep 1. So right now we have to keep 2, we have to keep 1. Okay, let's say now 4 comes into the picture. Let's see how the picture changes. So now when 4 comes into the picture, what we will see is that, okay, 4 is greater than this 1 which was there. So any subarray having 4 and 1, like if k was 3, k was 4, k was 5, doesn't matter. Any subarray having both 1 and 4 obviously will have 4 as the better answer, right? And if we think about it, any subarray that is supposed to have 1, right, and ends in the future, that subarray will obviously also contain 4, right? So if some subarray starts at anywhere before or equal to 1 and it goes up to somewhere in the future, that basically means that it will include this 4 and the answer can never be now this 1. So once we go past this 4, this 1 becomes useless, because now this 1 will no longer be a maximum, because any subarray going forward will contain this 4. Similarly, this 2 also becomes useless. Why? Because again, any subarray taking this 2 and going forward after 4 will obviously contain this 4. So as soon as we get a greater element, the smaller elements becomes useless. That is a very important point. Okay, so here the thing is that as soon as we get an x which is more than some y, right? And remember that y happened in the past, not in the future. Like because of this 4, this 3 will not get useless. Why? Because we are sliding the window forward. So there will be a point when this 4 gets out of the window, and there is a chance now that 3 becomes maximum. So as an example, if here there were just smaller numbers, so when 4 moves out of the picture, then 3 has a potential of becoming maximum, right? But when we talk about this 1 and 4, when 4 goes out of the picture, 1 would have already gone out of the picture, right? So whenever we get an x which is more than y and x occurs after y, then after this x occurs, y becomes useless, right? So let's again read these lines carefully. Y becomes useless. As soon as we get an x which is more than some previous value y. Second condition, this y which is smaller occurred before, right? X occurs later. So as soon as we get this x, then these y's become useless, because now any subarray having these x will always has y also. Okay. So the solution goes with this idea, the solution goes into this pattern that we can try to keep our elements which are useful and remove the elements which are useless. So what I'll do, let's just go over, okay. So let's just go over the original array and see how we'll go proceed about it. Okay. So basically what will happen, when I get 2, I'll keep it with me. Now I get a 1. It is smaller, but it can still become useful when 2 comes out of the picture. So I'll keep my 1. Now 4 comes. As soon as this 4 comes, we will remove our 1 and remove our 2. So actually what will happen? This 1 will remove, this 2 will remove, and I'll just put my 4. Right? So I remove my 1, I remove my 2, and I just put this 4. Okay. Next, 3 comes into the picture. I put 3. Okay. Let's take 0 and 1 now. 0, 1. 0 comes into the picture. I'll keep my 0. Because again, smaller. Right? Smaller we are keeping. Why? Because when 4 and 3 go out of the picture, it might happen that 0 becomes the maximum. Next, 1 comes into the picture. Before that, because our k is 3, we will see that as soon as 1 comes into the picture, 4 goes out of the window. So we have to remove this 4. Right? Because it goes out of the picture. Now we need to put 1. Before putting 1, we'll see that okay, 0 is there. 0 now becomes useless because we have a greater element. So any array containing 0 will in future also contain our 1. So I'll remove this 0 and I'll put my 1. Okay. So this is how the iteration will look like. Let's also see how we'll calculate maximums, right? So let me go back to where we started and do this once more, right? So I have my window size as 3. So first I'll take my first 3 elements and I have to insert them. So what I'll go 2, I'll go 1, 4 comes into the picture. We remove these 2 and put just 4. So if you think about it, this array, this second array only contains relevant, and the elements that are there in window. Like, because if they were not in the window, we would have removed them. If they were smaller, then also we would have removed them. So actually the front of my queue will contain the maximum. So actually if you see, the maximum is 4. Next what happens? I get a 3 in the next window and I push it. So I push my 3. Still maximum is 4 because we are considering this part. When 3 has been included, still the maximum is 4, which is the front. Okay. Next step, we move one more step forward. Now we have to take this 0. So again put 0, but still the maximum is 4. Okay, so we have got 3 windows so far. The maximum has been 4. Next, we shift the window. First thing we do, we remove this 4 because it has moved out of the window. Take this one and have to put it at the back. Before putting at the back, we'll remove the elements which are useless. So I'll remove this 0, I'll put 1, and this time the maximum which is at the front is 3, which you can see. Okay, right? So this is how the algorithm is proceeding. Basically what you do, anytime you want to take an element and insert, first see if new elements have been removed from the window, like we have shifted the window. So if there are some elements that need to be removed, remove them. Step 2, if there are some useless elements which are smaller, remove them also. Then put your element inside the data structure that you have. Okay. Let's think about these operations, right? So first we need to remove elements out of window. Right? So we are inserting some elements and we are removing some elements. If you think about it, the elements that we are removing are the ones that were inserted first. So it kind of looks like FIFO, right? That okay, 4 got inserted, then 3 got inserted, then 0 got inserted. Now, because window is shifting, 4 will be removed. So kind of like FIFO, remove from the start, which are now out of the window. But it is not just simple FIFO because we are also removing those elements which are small, right? And if you think about it, while putting an element, we remove the elements which are smaller and then put this. That means the last element pushed is always the smallest, right? The last element pushed is always the smallest. So that means this data structure that we are maintaining is always sorted in reverse order. If you actually see, we put 2, we put 1, sorted. We remove 1, we remove 2 and then put 4, still sorted. We put 3, 4, 3, still sorted in descending order. Then we put 0, 4, 3, 0, still sorted. When we are putting 1, we remove 0 and we put only 1. So again, sorted in descending order. Why? Because anytime we are putting an element in, we are making sure that smaller elements are removed. So it is in sorted order. That means the smaller elements that we want to remove, they will be at the back. So we don't just want removing from the front, but we also want removing from the back. So the operations important for us are pop front, remove from front, pop back as well, remove from back. And whenever we want to push it only at the back side. So push back as well. So if you think about it, our stack is push back, pop back, like insert and remove, LIFO. Our queue is push back, pop front, so FIFO. But here we want a combination. So therefore we use something known as a double-ended queue or DQ. So what is a double-ended queue? So if you have heard of something like doubly linked list, you can imagine it just like that. You have front, you have back, right? So removing from the start is also easy. How do you remove from the start? You just remove it and put the element here. Removing from back is also easy because you have a back pointer. Remove it and just put it here. So yeah, and pushing at the back and pushing at the front is also easy. So Double-ended queue is like a hybrid where it gives you capability to push pop from front, push pop from back. Okay. A few questions that might come to your mind is why don't we always use this? Why do we ever have to go to stack queue or anything like that? So the answer for that is this is more memory heavy. As you can clearly see, there are more pointers being maintained. So it is memory heavy. Another thing, in DQ, just like vectors, we can do V of I. So if you are aware of stack or queue, you cannot typically do queue of I or stack of I. You just take elements from top. But in double-ended queue, it's actually very much possible to access randomly an element in the DQ. Similarly, other capabilities of vector are also available here. For example, if you ever want to have a sorted DQ and find a particular element, you can use lower bound, upper bound, right? So anything that is there overall in vector mostly is available in DQ. That is possible because we have random pointers also in the middle. So apart from having the front and the back, there are some random pointers. So constant wise or time wise, this is worse than using a vector. So whenever you want to use a vector, use a vector. Don't go for DQ. But it's good to know that this also has those capabilities. So if you want pop front, pop back, so vector also doesn't have pop front. Like if you remove the first element, it will take more time. So whenever you want to have pop front, pop back and push front, so all the four, plus you want random access, plus you want sorted may lower bound, upper bound, anything and everything can be available with this data structure. Cool, then let's talk about code part now. So remember, just to forget, like if you have lost so far, the idea that we went ahead with, anytime we are going through elements, we are trying to insert. Before insert, first we remove anything that is outside the window. Then we remove anything that is smaller and then push it. And every time at the front, we will get our maximum. So yeah, let's get into our code. Submissions. Let's take this. Okay. So what I've done, I've written two functions to insert and to remove, right? So let's look at both the functions first and then we'll go into the code. So what does this insert do? This inserts take my vector and an index that, okay, I want to insert nums of I inside this double-ended queue. So before inserting, we need to remove the elements from the back. So what I've done, I've written a code here that till the time my double-ended queue is not empty and the element that we get from the back, so nums of dq.back. So in a double-ended queue, we are storing the indices, not the elements, indices. So dq.back will give us the last indice. So if the nums of last index is less than nums of I, so that means the new element being inserted is, let's say 2 and the last element inside is, let's say 0. So you'll remove that 0 and then put this 2. So till the time the element at the back is smaller, you do pop back. You keep on removing the elements from the back. Then finally you push back your I. That, okay, this index is now being inserted. So that is the idea of insert. Remove the elements which are smaller and then put the new element. This removes from the front those which are outside the window now. So what I've done, I have passed the k, which is the size of the window. I have passed the index that we have reached and I have passed the dq. So till the time the difference between the index that we have reached and the front element in the front, if that is more than or equal to k, that means this element needs to be removed from the window, right? So for example, right now if we are at index number 5, k is 3 and let's say the one in the beginning is 0. So 5 minus 0 is 5, which is more than or equal to 3. So we have to remove it. So till the time the element at the front is at more distance than k from this index, till that time you keep on doing pop front. So remove the elements from the beginning. Actually, if you think about it, because we'll be calling this at every moment, We just have to write an if. Don't actually need a while here if you actually think about it. But yeah, just to make it generic, I have written a while loop. Like, because anytime we move the sliding window, we are just going to at max remove one element. So yeah, this is actually O of 1, just removing one. But yeah, just to keep it generic, I've written this like a while loop. Okay, so let's go to this max sliding window and let's see what it does. So first thing that we are doing, we are going over the first k elements and inserting them into our DQ. So first k, directly insert. Now, after inserting first k, the front of the queue will have your first maximum. So I have pushed nums of front into the result. Now we go from k to end. Every time we'll remove, if possible, one element from the beginning, remove from the end, and then insert. So I have done two things here. Remove if there are some elements at more distance than k from this I, right? So remove all of those from the beginning. Then insert my ith element, and finally you push back into my result whatever is in the front, because we have calculated a new window, and for that new window we'll have in the front the result. So I'll push that back. Okay, so this is how it is going. Let's also talk about the time complexity. So remove we already know is O of 1. Okay, but this monotonic insert, some of you might think that it is a while loop, so it might go to n square. But if you think about it, what is happening is every element would get inserted once into the double-ended queue and only get removed once. Like, even if it's getting removed from the back, now it will never return. So for every element, we are just doing two operations. Once we are inserting, second we are removing. Either it will get removed from the front or it will get removed from the back. So actually total operations are just going to be 2 into n, because the total code is just inserting and removing. Okay, so that is why the time complexity of this code that we have written is going to be O of n. Cool, then that was the question about double-ended queue. This is a common pattern. This is also known as monotonic structures. So let's just have some concluding remarks. So if you have been enjoying the concept so far, just make sure that you give the video a like. Let's just conclude with some remarks. And yeah, if you're new here, do subscribe to the channel. So yeah, a common pattern on these data structures are the monotonic patterns. By data structures, I mean stacks, queues, and DQs. What does monotonic means? Keeping the elements in a decreasing or an increasing order. So a lot of questions on stack also, you try to keep the elements in increasing order. For example, one good question for that is next greater element. Similarly, there are questions in queue where you try to keep a monotonic queue. Similarly, there are for DQ. For DQ specifically, the main questions forms where this becomes applicable is when generally you would have used a queue. So there is a window, or there are some elements that are getting pushed and there is an expiry of those elements. So when they get removed from the start. So generally it would have been possible to solve it via queue. But to optimize it, you try to remove some unnecessary elements from the end, right? This is a common pattern that we will see in future questions as well, that generally it's a queue, but to remove some useless elements that are there at the end before inserting, we go with DQ so that we have that capability of removing from the end. Great, then let's do 2-3 more problems in the coming days on this particular pattern. And yeah, just keep coding, make sure that you make good progress. This is a pattern which is commonly used in tougher problems. Like there are a lot of hards on this particular pattern. But yeah, a fun pattern to enjoy. Great, then see you guys tomorrow. Bye bye. Good night.